In this video, we will talk about the sampling distribution of the sample proportion. Let's start by talking about how we can use the normal approximation to the binomial distribution. So we have learned before that if a Bernoulli trial is repeated n times, then the number of successes x out of n trials follows the binomial distribution. That is, x follows the binomial with parameters n and p. Now, when n is sufficiently large enough so that n times p is at least 10, and n times 1 minus p is at least 10, it has been shown that x will be approximately normal with a mean equals to n times p and a standard deviation equals to the square root of np times 1 minus p. Let me illustrate this with an applet. So this is an example where you have a binomial distribution with 6 trials. So the possible number of successes would be 0, 1, 2, 3, 4, 5, or 6. And the success probability here is 0.5. And if you look at the histogram, the probability histogram of this binomial distribution, it is symmetric. That's because the probability of success is 0.5. And so it looks more or less like the normal distribution, right? However, if p is not 0.5, for example, if p is smaller, you will notice that the distribution is no longer symmetric. It's skewed to the right now. And if the success probability is higher, closer to 1, then it will be skewed to the left. But if you increase the sample size, notice that even if you started with a success probability of 0.75, the probability histogram becomes more and more normal looking when n increases. And that is basically what this one is saying. When n is sufficiently large, x, which is really binomial, can be approximated by a normal. Let me give an example. So suppose we let x be binomial n equals 10 and p equals 0.4. So this is actually an example where n is actually not large enough. It's not sufficiently large because if you multiply n times p, we only get 10 times 0.4 is 4. That's not even bigger than 10. But I want to show you that even if n is not that large, the approximation we get using the normal density is actually pretty good. And if you satisfy those two conditions, then your estimates will be even better. So let's try to calculate the probability that x is less than or equal to 5. We can do this using the exact binomial distribution because we know x is binomial. And so we can just use the calculator. Remember, there's this binom CDF to calculate the capital F of 5, which is the probability that x is less than or equal to 5. So you specify the n, so 10, the probability of success 0.4, and x, which is 5. And we get a value of 0.834. So that is the approximate probability that x is less than or equal to 5. And in terms of the histogram, so if this is the possible values of x, so 0 up to 10, successes out of 10, right? And here, we want to find the probability that x is less than or equal to 5, which is essentially the sum of the areas of those 6 rectangles. Rectangle 0, 1, 2, 3, 4, and 5. So if you sum the areas, that will give you this. Remember, we said the area of the rectangle is actually the probability. So now we're going to try to calculate this same probability, but treating x as if it's normal. Let's try to do this using the normal approximation. And I'm going to talk about this continuity correction in a while. So what I'm going to do here is I'm going to use the result from up here. So if we assume that this is large enough, then we say x will be approximately normal. The mean will be n times p. So n times p is the mean of the binomial. So n times p, it gives you 4. And that's the standard deviation of the binomial, which is the square root of 10 times 0.4 times 0.6, giving us a value of about 1.55. And so if I want to find the probability that x is less than or equal to 5, I could do that using stat key. Right? So if I go to stat key, go to normal, and change the mean. So the mean is 4, and the standard deviation is 1.55. So 1.55, and we want to find the probability that x is less than or equal to 5. Okay, so if we do that, we get a probability of 0.741. So that is our probability. And you can also do this using the calculator. Remember, the normal CDF. and I got 0.741. Now if you compare that to the actual value, the exact value, I mean, it's not that far, but it's not really a good estimate at this point. Basically what we did here is we try to get the probability, or we try to estimate the total area of those rectangles using the region under the density curve of the normal, under this red curve here, starting from 5 and everything to the left. That's what we did. If you look here, right, everything to the left of 5. And if you notice, the area to the left of this point includes, say, this portion here and this portion and this portion that's not really supposed to be included because they're not part of the rectangles. But that's okay, because if you notice, we actually missed some corners of the rectangle as well. So those corners that we missed and this additional region that we included, they kind of cancel out each other. But the problem really with the approximation of the normal here is because 5 is right in the middle of that rectangle 5. And so when you get the area to the left of 5, we ignored half of rectangle 5. So this upper half here was totally ignored. So if we want our estimation to be better, then maybe we could adjust the value of x. Instead of using 5, we use 5.5. We move half a unit to the right, and that would include the entire rectangle 5. And let's do that. That's what the continuity correction is. So using the normal approximation with continuity correction, this continuity correction is essentially saying add 0.5 to the value of x. So in this case, if we go back to StatKey, rather than using 5, if I use 5.5, look at the value that I get to the left. It's 0.833. And you can also get that using the calculator. So if you get the area from, say, -10 to 5.5, you get the probability of 0.833, which is much closer to the actual value than the estimate we had without the continuity correction. So when do we use this continuity correction? We only use this when we are treating a binomial random variable as if it's normal. Okay. So when we are trying to get the area of rectangles using the density curve of the normal. That's the only time we do this. When we are approximating a discrete variable with a continuous one. So let me give you the different cases that you will encounter to do this. So when estimating the binomial probability using the normal density, for case 1, so this is what we observed, if you want to find the probability of a binomial random variable that it is going to be less than or equal to some value, say 5, then that will be approximately equal to the probability of that random variable, treating it as if it's normal, but you adjust the value by adding it by 0.5. Now what about case 2? What if I want to find the probability that it's strictly less than 5? Well, we just write that this probability that x is less than 5 is equal to the probability that x is less than or equal to 4. Right? Because if x is binomial, that means the possible values of x would have to be integers. And so if it's less than 5, it has to be at most 4. Because values like 4.5 and 4.6 do not get any probabilities under the binomial. And so from here, this is now a case 1 format. So we say this is going to be approximately equal to the probability that x, treating x as if it's normal, is less than or equal to 4 plus 0.5. So the idea is to just convert the problem into a less than or equal to, and then add the 0.5. Okay. So case 3. What if I want to find the probability that x, again a binomial quantity, is at least 5, greater than or equal to 5? Then I'm going to convert that problem into a less than or equal to problem. I will use the idea of the complement, so that is equal to 1 minus the probability that x is less than or equal to 4. Right? The complement of getting 5 or more is if you get 4 or less. And then we say this is going to be approximately equal to 1 minus the probability that x, treating x as if it's normal now, is less than or equal to 4 plus that 0.5. And the last case is, what if I want to find the probability that x is between 3 and 5, including the endpoints 3 and 5? Well, for this one, I will just write this as the probability that x is less than or equal to 5. So all the probabilities from 0 to 5 minus the ones that I don't need, which are the probabilities from 0 to 2. And then I will approximate them by treating x as if they're normal but adjusting the values of x by adding 0.5. So let's see an example. An unnoticed mechanical failure has caused 1/3 of a machine shop's production of rifle firing pins to be defective. If an inspector will check 90 randomly selected pins from this batch, what is the probability that the inspector will find, letter A, no more than 25 defective pins? So I gave a hint here. Before calculating the probability, check first that you satisfy the required conditions. So in this problem, I would like to use the normal approximation to calculate this probability. So first, note that if I let x be the number of defective firing pins out of 90, so take note, each firing pin can either be defective or not. So it's a Bernoulli trial. The chance it's defective is 1/3. It's always going to be 1/3. And then you repeat this 90 times. And so we know that x is going to be binomial, binomially distributed. And the parameters are n equals 90 and p is 1/3. So now I'm going to check if I can approximate this with the normal approximation. So we check. These are the two conditions. Is n large enough so that n times p is at least 10? Let's see. N times p in this case, n is 90, p is 1/3, giving us a product of 30. That is bigger than 10, so that's good. And the second condition is n times 1 minus p. So in this case, 90 times 1 minus p is 2/3, is equal to 60. Again, that is bigger than 10. And so therefore, we can say that x is approximately normal with the mean equals to n times p. So the mean is n times p. In this case, is 30. And the standard deviation is the square root of np times 1 minus p. So np times 1 minus p, giving us a standard deviation of about 4.47. So if we want to get the probability that the inspector will find no more than 25 defective pins, we could use stat key. So in this case, I want to find the probability that x is less than or equal to 25. And then I'm going to approximate it by treating x as if it's normal, but then I have to adjust the value of x, right, by adding 0.5. So using stat key, you can edit the parameters. So the mean is, what's the mean? 30, and the standard deviation is 4.47. So 30, standard deviation is 4.47, and we want to find the area to the left of 25.5, giving us an area of 0.157, and that's how I got that. Or you can also use the calculator, so use the normal CDF, and since the lower limit is not provided, I just use a large negative number here. Okay, up to 25.5, that's the mean, and that's the standard deviation. Alright, so for part B, what is the chance that the inspector will find less than 25 pins? So this one looks very similar to A, but this one is saying strictly less than 25. So that means it must be less than or equal to 24. So again, using the continuity correction, we can say that this probability will be approximately equal to the probability that x, treating x as if it's normal, is less than or equal to 24.5. So we can go back to stat key and just change that to 24.5. And we get the value of 0.109. That's how I got it. Or you can again use the calculator if you like. Now, if you use the exact binomial probability, you notice you will get a value of 0.108. Not very far from our approximation. Okay. Part C. What is the chance that the inspector will find at least 20 defective pins? Meaning x is at least greater than or equal to 20. So this is case 3. We're going to use the complement. So this is equal to 1 minus the probability that x will be less than or equal to 19. That's the complement of getting 20 or more. And we say this will be approximately equal to 1 minus the probability. Again, we treat x as if it's normal, but then we have to do the continuity correction and add 0.5. And so if you use stat key, change that to 19.5, you get an area to the left of 0.0094, and that's where I got that. So subtract it from 1, you get a probability of 0.9906. So if you use the exact binomial distribution, then that probability would be 0.9923. Again, very close to our approximated value. So maybe you're wondering, so why do we have to do this using the normal approximation if we can get the exact probability using the binomial? The reason why is because we actually use this idea later on to test for proportion, and so I'm introducing this idea that you can approximate the binomial with a normal here. So what about letter D? What is the probability that the inspector will find between 22 to 34 inclusive of the endpoints, defective pins? So you want to find the probability that X will be between 22 to 34. So remember, the way we calculate this binomial probability is we get the sum, the cumulative probability up to 34. So all the probabilities from 0 to 34. And then we subtract the probabilities that we don't need, which are probabilities from 0 to 21. Take note, it's 21, not 22, okay? And then we say now, because we want to approximate this with a normal approximation, we say we treat X as if it's normal, but you have to add a 0.5. Okay? And so we can easily get this probabilities using stat key. So this is 34.5, and you get an error to the left of 0.843. 0.843. And if it's 21.5, you get 0.029. 0.029. Okay. If you use the exact distribution again, you get a value which is really, really close to what we got for the using the approximation. All right, so now it's your turn to practice. Try to answer these questions and pause the video. Only continue when you're done. Okay, so here are my answers. So for part A, you want to know what is the exact distribution of X. In this case, X is binomial. That is the exact distribution. And here is 500. That's the number of drivers they sampled. And the success probability here is 0.4. So for part B, we want to verify if we can approximate this using the normal distribution. And if so, give the parameters of the normal distribution. So to check, we need to check the two conditions. So the first one is that n times p needs to be at least 10. So here 500 times 0.4 is 200. Yep, that's bigger than 10. And the second condition is n times 1 minus p. So 500 times 0.6 is 300, bigger than 10 as well. So both are bigger than 10. And so therefore we can say X is approximately normal in this case. Mu is n times p, which is 200. And the standard deviation is the square root of n times p times 1 minus p. And you get about 10.95. And you can use stat key to calculate these probabilities. Okay. Now let me talk about the sampling distribution of the sampling proportion. And to do this, let me give you a review. So remember, if we have X following a binomial distribution with parameters n times p, this is the probability distribution function. We know that the mean of the binomial is n times p, and the variance is given by np times 1 minus p. And so therefore, if you want to get the standard deviation, you just take the square root of that. That is the standard deviation of that binomial. Now, if you note, the sample proportion is actually just the number of successes out of the sample divided by n. And so if you want to get the mean of p hat, you just get the mean of X divided by n, and that is why the mean of p hat is p. And if you want to get the standard deviation of p hat, you just get the standard deviation of X and then divided by n, and so you get the standard deviation of p hat is going to be the square root of p times 1 minus p over n. And there is a central limit theorem for the sample proportion. So if you draw a simple random sample of size n, binary or dichotomous responses from a population with a proportion of success p, when n is sufficiently large, the rule of thumb they like to use is that n times p is at least 10 and n times 1 minus p is at least 10. The same conditions I had before where we approximate the binomial using the normal. So the sampling distribution of the sample proportion p hat is going to be approximately normal. So this is very similar to the central limit theorem for the sample mean, where we said if n is sufficiently large, in that case there, when n is greater than 30, x bar is approximately normal. Here, we're saying that when n is sufficiently large enough so that n times p is at least 10 and n times 1 minus p is at least 10, then p hat is also going to be approximately normal. So that is, p hat is going to be approximately normal. The mean of p hat, we said, is equal to p, and the standard deviation is equal to this. Okay. So the central limit theorem is really about the normality of the distribution. not about the mean and the standard deviation. Those two can be obtained using algebra. So again, it is about the normality of the distribution of p hat. Now let me give an example. Suppose we assume that 10% of the UWL student population are left-handed. If we select a random sample of 300 UWL students and calculate the sample proportion p hat of these students who are left-handed, then what can you say about the distribution of the sample proportion p hat? Explain why. So in this case, we first have to check, do we have a large enough sample here so we can apply the central limit theorem? So we check. We know that n times p is 300 times 0.1 is 30, that's bigger than 10. And n times 1 minus p is 300 times 0.9, which is 270, that's bigger than 10 as well. So we can use the central limit theorem for the sample proportion. So by the central limit theorem of the sample proportion, p hat is going to be approximately normal. The mean is equals to p, the success probability, which is 0.1 here, 10%, and the standard deviation is the square root of p times 1 minus p divided by n, which is about 0.0173. And so with this, we can now find the probability that the sample proportion will be less than 12%. So in this case, because p hat is normal, we can just go to our stat key, right, and change the parameter value. So what's our mean? Our mean is 0.1, standard deviation is 0.0173. So 0.1, this is 0.0173, I believe. Yep, okay. And what we want to find the probability that it is going to be less than 12%. So less is left tail, change that to 0.12, so 12%. And we get a probability of 0.876. So that's how I got this. So the probability that p hat would be less than 0.12 is equal to 0.876. And of course, you can use the calculator as well, using the normal CDF function. What about letter C? What is the probability that the sample proportion will be at least 15%? So all we have to do, go here and click right tail. I want this to be 0.15%, on the 0.15 or 15%, and there it is. The area to the right is 0.0019, and so that's how I got this 0.0019. The probability that p hat is greater than or equal to 0.15. And again, you can use the calculator if you like. And part D, what is the probability that the sample proportion is between 12% and 15%? So we can just go back and check our plot in StatKey, and if you want to get a chance, it will be between 0.12 and 0.15. That's the area in between these two. It's 0.122. And so that's how I got this, 0.122. Okay. All right, so now it's your turn again to practice. Try to answer these questions. Pause the video and only continue when you're done. And here are my answers. So for part A, if you check the conditions, n times p here is just 4 and n times 1 minus p is just 6. Neither one is bigger than 10, so we cannot use the central limit theorem. So in this case, we actually need at least 25 values, so that when you multiply 25 times 0.4, you get at least 10. In part B, when n is 100 and p is 0.6, both n times p and n times 1 minus p are bigger than 10, and therefore we can use the central limit theorem. Therefore, p hat here will be approximately normal. The mean is 0.6. The standard deviation is about 0.049. In part C, when n is 40, p is 0.9, n times p is 36, so that is bigger than 10. That's okay. But n times 1 minus p is only 4. So since one of them is not bigger than 10, then we cannot use the central limit theorem. You need to satisfy both conditions for you to be able to use the central limit theorem. In this case, p is 0.9, the probability of success, but the probability of failure is 1 minus p, which is 0.1. Because of this, we need at least 100 values to satisfy both conditions. And from part D, use the information from part B to calculate the probability that p hat will be lower than 50% or at least 75%. So I just use StatKey to do this. So I have the mean, the standard deviation, I got these values. All right, I hope you got all the answers right.